Hi, welcome to part 2 of my Bitcoin primer for the layman. This primer consists of 4 parts. Part 1 explains what is Bitcoin and how it works. Part 2 covers the cryptography in Bitcoin. Part 3 takes a look at some major issues of Bitcoin. Part 4 reveals the 9 fallacies of Bitcoin. The links to the 4 parts are in the description box below. Now let's get into the crypto and cryptocurrencies. First, a bit of perspective so you can appreciate today's technology on security protocols and data transmission. In the days of telex machines, banks sent each other important messages using test keys for authentication. These were messages with legal liabilities, such as payment instructions, opening of letters of credit, etc. In order for two banks X and Y to be able to do this, they must have a test key arrangement. If Bank X desires to have a test arrangement with Bank Y, X sends to Y 2 separate items. First item is the fixed key. This is a secret code number which is fixed, one for X and one for Y. The banks are in possession of each other's number which are to be used exclusively between the two of them. The second item that X sends to Y is a booklet containing a set of variable numbers. The booklet contains codes for variables such as dates, values, currencies. Some may have a code for serial numbers. X has testing arrangements with other relationships. With each counterparty, they have exclusive fixed code. The booklet for variable codes is common for all parties. When Bank X and Y send any important messages to each other, they apply the codes according to the variables in the message. The code values are aggregated with the unique fixed number, to arrive at a key. The total number is the test key which was indicated in the message. To authenticate, the receiving bank did the same computation. If it arrived at the same test key number, the message was authenticated. On such a simple testing basis, trillions of dollars were moved around the world daily. Note that this merely authenticated the variables and the sender. The message text itself was not encrypted. Thus contents in the message may corrupted. Example, if it was a payment instruction, the name of the recipient or bank account number may have been changed. Coded messages in the military are different. It is the text itself that is coded. "We will attack at 3 p.m." might then appear in some gibberish text. This can be done manually, but smart code breakers will have no problems with this. In World War II, the Germans came up with a cipher machine called Enigma. When an alphabet key is hit, a different character is typed. To decipher, simply type the character shown, and the correct alphabet will be typed. Behind the contraption is very deep mathematics and complex formulas. Despite the complexity, the Polish intelligence managed to crack the code. They shared this with British intelligence, who went on to crack further versions of Enigma. The capability to decode Nazi secrets helped the Allied forces significantly in the war. It played a critical role in identifying where German submarines will attack commercial shipping. Allied destroyers could then locate the submarines and destroy them. Thus lives were saved and supply lines kept open. Those were the days of analog data. Today, we have binary data, represented in the dual state of 0 and 1. With computers, encryption technology for data security has taken to new heights. Cryptology is the science behind all this, and it applies deep mathematics such as numbers theory, abstract algebra, probabilities, computer science, etc. There are now several software we call algorithms that perform these functions. We will meet some of these in Bitcoin system. How do we send secured data digitally today? Today it's done with an electronic signature or a digital signature. What is an electronic signature? When you send someone a hard copy document, with your handwritten signature, you legally bind yourself to the document. But when soft copies are transmitted, there is no handwritten signature. Electronic signature is intended to ensure the validity and legal effect of contracts entered into electronically. What is acceptable is governed by the legislation of each jurisdiction. E-signature is defined as electronic sound, symbol, or process, attached to or logically associated with, a contract or other record, and executed or adopted, by a person with the intent to sign the record. Soft copies of documents can be signed with various electronic signature software like Word, Adobe, Sign Now, DocuSoft, etc. With hard copies, you may sign the document, but your signature may not mean anything if the receiving party does not know you. So you go to a minister of oath to get the document notarized. With soft copies, You can have a secure electronic signature by using a trust service provider, where a digital certificate can be obtained. The certification authority uses digital signature technology to provide you with a way to append your electronic signature on your documents. Just to stress again, electronic signature is about legality. The sender binding himself to the message sent. Digital signature, on the other hand, is about message integrity. That the message truly came from the sender and nothing in the message has been corrupted. Before we turn to digital signature, we need to understand a mathematical function called hash which lies at the heart of cryptology. There are two applications of hash which are quite different. One relates to the creation of hash to form hash tables used in structuring data storage. This is not our concern here. Our hash is an algorithm, or mathematical function, to transform or encrypt a message. The message is the input, and the algorithm churns out an output of what looks like random alphanumeric characters. This output is called the digest, tag, fingerprint, witness, or hash. The input is variable length and the output is a fixed length, depending on which algorithm is used. For example, secure hash algorithm 256, or SHA-256, will generate a hash of 256 bits. It is near impossible to decipher the hash. A minor change in the message, such as a single character, a punctuation mark, a spacing, etc., will generate an entirely different hash. Thus no two different messages will produce the same hash, i.e., it is collision resistant. We can say hash is the fixed size alphanumeric representation of a message that has been transformed by a mathematical algorithm. Now let's get into digital signature. Digital signature is a way for a person to send a message electronically to another person, and allowing the recipient a capability to verify the message. Verification means determining the sender is who he is, and the message has not been tampered. It is not meant to hide messages, unlike in military intelligence work. So it basically serves the purpose as in the bank's manual test keys, but in a much far superior way, using very complex mathematical computation which also assures the message itself has not been tampered. To do this, both parties must of course be using the same software platform. Digital signature is based on asymmetric cryptography, which uses the public key infrastructure, or PKI technology. It is a process that uses a pair of related keys. A private key that is used to encrypt, or sign, and a public key to decrypt, or authenticate, a message. Examples of PKI protocols are Ribest-Shamir-Alderman, better known as RSA, and the digital standard signature, known as DSS. To generate the private key, the user inputs a random text to a cryptographic hash function, let's say RSA-256. The algorithm generates a hash of a fixed length. This is the private key used to sign a message. The private key is hashed again to generate a fixed length public key that is used to authenticate a message. The public key is shared with all parties the user wants to send messages to. The private key is secret to owner. When sending a message, which is of variable length, it is first hashed using, say, SHA-256. This transforms or encrypts the message to produce the message hash. To sign the message hash and the sender's private key is input to the PKI algorithm to generate the digital signature, which is simply a string of alphanumeric characters, which is really also a hash. So basically, digital signature is a double hashing paradigm. The digital signature algorithm computes on the cryptographic hash instead of the actual message. This is easier as the algorithm is working on a fixed size hash. With collision resistance, no two messages will produce a similar hash. Thus, no two messages will produce a similar digital signature. The sender then transmits his public key, the digital signature and the original message to the recipient. Note that there is no attempt to hide the original message. The recipient uses an algorithm to apply on the original message, sender's public key, and the digital signature. The system does some heavy mathematical computation, which is the verification process. It then indicates a yes or no answer. A yes confirms the original message indeed came from the sender, and that the message has not been tampered. The recipient can verify the message without knowing the sender's secret private key. This is made possible because the private key has been mathematically embedded in the public key. Once verified, the digital signature binds the sender to the original message received. It is as good as, if not better, than a handwritten signature. This is the fundamentals behind the data transmission of Bitcoin, which makes the system very secure. When you send a transaction, they are digitally signed and verified by the full nodes. Bitcoin wallet. To send or receive Bitcoins, you need to have a Bitcoin wallet. The Bitcoin Core is open source, so anyone can design a wallet for use on the system. The vendor does not matter. The wallet operates independently of the Bitcoin Core. We'll just call it Bitcoin Wallet. The wallet is the app that generates three important unique codes: your public key, private key, and address. Private key. The wallet app generates your private key. In order to generate the key, we need to input some text. This text that is input for the wallet to create the private key is called the seed. A seed is any string of characters, but it is important to be as random as possible. Some systems auto-input the seed. Others allow you to manually input any characters you want. To be very secure, most developers use a random number generator. The number generator has to be one that is powerful enough for cryptography work. This is called a cryptographically secure pseudo-random number generator, or CSPRNG. Once the seed is obtained, it is hashed with RSA-256 to generate the private key. The private key is represented in 64 hexadecimal characters of 4 bits each, making its size 256 bits. The CSPRNY generator is deterministic, which means that the same seed will always generate the same private key. No two different seeds will ever generate a similar key. A tiny change in the seed will generate an entirely different private key. It is almost impossible for someone to guess the private key. A brute force attack will require a very powerful machine and hundreds of millions of years to hack a private key. The private key has three functions. 1. It links you to all your bitcoins in the system. 2. It is used to generate your public key. 3. It is used to hash the Bitcoin transaction, or message, to generate the digital signature. Whenever you send a Bitcoin transaction, your private key is used to sign it to produce the digital signature for the message. Public key. The public key is generated by hashing the private key firstly by the elliptic curve digital signature algorithm, or ECDSA. This is a one-way encryption. There is no reverse process, which ensures the public key is 100% safe and can be shared with anyone. It is then hashed again with SHA-256. The private key public key is related to the private key that created it. They are paired. The private key has been mathematically embedded in the public key. The public key looks something like the private key in 256-bit hexadecimal format of 64 alphanumeric characters. The public key has two functions. 1. It is used to generate your Bitcoin address. 2. It is used by miners to verify your transaction. When you make an output transaction, your public key is also sent over. The miners use your public key to verify the message. If the verification is a success, the full nodes are sure that only you, and no one else, could have sent the message. They perform the verification without knowledge of your private key. Your Bitcoin address. This is not the mailing or residential address. It is your identifier. Much like your code name to the system. To generate the Bitcoin address, the public key is first hashed with SHA-256. It is then hashed with algorithm RIPEMD160. At this point, the hash is a 64 hexadecimal code which is difficult to read. The address is the code that users need to input when using Bitcoin system, thus the need for a more user-readable code. In order to make it more user-readable, it is further hashed by algorithm base58, which generates a 34 alphanumeric code. Base58 also encodes some checksum functions to detect input errors. What is the purpose of the Bitcoin address? The Bitcoin system does not hold any personal information of users. There is no registration of your name, mailing address, contact numbers, etc. It works completely in privacy. So how do we to transact with each other, and how do we know what Bitcoin balances we have in the system? The answer is the user's address. It's your identifier on the system which you share only with parties you deal with. This is the only info you share with the rest of the world. In the Bitcoin ledger, only your address is shown. The Bitcoin system does not know anything else about you. The public can only recognize your data if you have dealt with them and they know your address. When you use your wallet, you can view the unspent TXO in the system under your address. You send bitcoins to someone by indicating that person's address. Similarly, others send bitcoins to you using your address. Obviously, the receiving party has to advise his address to the paying party. So the address in a transaction is like the payee name on a check. Just like when drawing a check, you want to make sure the payee name is written correctly, so in Bitcoin, you want to make sure the address is filled without error. A wrong address may end up with money being sent to a wrong party. To minimize errors, merchants may use a QR code for their customers to scan instead. What's actually in the wallet? The Bitcoin wallet is simply a software. It contains a file that holds the paired private key and public key, which are 64 character codes. There are no bitcoins in the wallet. Lose the private key and you lose your bitcoins. The only way an owner can spend his bitcoins is with his private key. In banking systems or other applications, the loss of passwords is not a big problem. It can be reset because personal info is in the system. For Bitcoin, only the private key ties the owner to his coins and the key is kept independent of the Bitcoin core system. Thus, if the private key is lost, the owner loses his bitcoins forever. There have been many such tragic instances. There are various ways that wallets can be used, which balances conveniences versus security. They are called hot wallets, which are basically online connection to the network, and cold wallets, which are offline. You can use special physical gadgets to store the private key, put it in a bank vault, burn it and embed it in your brain, etc. It can be stored in a USB, offline computer, some service providers, etc., but these can be damaged or stolen. There are many options, but we won't go into details here. Let's look at cryptography technology at work in Bitcoin payment transmission. Alice wants to use Bitcoin to pay for the pen that cost 50 Bitcoins. Alice accesses the Bitcoin system using her mobile. Her Bitcoin wallet app allows her to check the number of unspent Bitcoin she has. She sees 3 UTXO of BTC 20, 30, and 80. Alice decides to use the BTC 80 coin to pay. She obtains the vendor's Bitcoin address by scanning the QR code from a promo brochure. She fills up the output transaction and requests for refund of BTC 30. Then she clicks send. The Bitcoin system computes a digital signature by hashing Alice's private key in the transaction message. The system transmits the transaction, that is, the TXO, together with the digital signature, and Alice's public key. This is broadcast to the system. Full nodes pick up the transmission and verifies it. The verification is done by checking compliance of various criteria set by the system, which includes the authentication of the transaction. Full nodes authenticate the transaction by using the Alice's public key, the digital signature and the TXO message. If validation fails, the full nodes reject the transaction. If it passes, full nodes keep the transaction and the mempool in their server. This is basically how cryptography technology works in the transmission of messages in Bitcoin, which provides full integrity assurance. Now let's look at what the much publicized Bitcoin mining is all about. Miners serve 3 basic functions. 1. Verify and propagate transactions as part of their full node responsibility. This has been explained. 2. Build new blocks of transactions. This is what will be explained here. 3. Miner whose block is approved is rewarded with some new bitcoins generated by the system. This is analogous to new coins being mined. First, on how miner picks transactions. Our miner is Max. He creates a candidate block. This is a work-in-progress block, not yet approved. From his own server, Max picks new verified TXO from mempool and transfers it to the candidate block. What transactions does Max pick? First, the block has a size constraint. It is not more than 1 megabyte. At the moment, average number of transactions in a block is about 2,759. Second, he has to allocate about 50 kilobyte for priority TXO. Lastly, the balance he picks according to his focus. He may want to be selective and pick those with higher fees first. As speed is of essence, he may simply pick as fast as he can, disregarding transaction size and fees. Next, Max will do a series of hashings with the transactions. As a full node, Max would have already verified all the transactions in his server mempool. It would be foolish not to do so because his block will be rejected if a transaction in his block has not been verified, thus wasting all his effort. Max then performs a series of hashing functions on the TXO. Bitcoin uses the SHA-256 for this purpose. TXO are paired and hashed. After which, the hashes are paired and hashed again to produce a further hash. The process of pairing of hashes and hashing them continues until one final hash is derived. This is called the Merkle root. Hashing secures all the transactions. Any attempt to hack into transaction data will invalidate the hash and will be exposed. Having done all this transaction hashing, the miner then proceeds to perform proof of work done. The miner hashes the Merkle root with the header of the previous block, to produce the hash for the candidate block. This candidate hash is compared to something called the targeted number. The objective for Max is to obtain a candidate block hash which has a value that is equal to, or less than, the targeted number. This is the mathematical problem that miners race to solve. It requires powerful computing capabilities, huge investments and burning up electricity bills. If Max is the first miner to obtain the right hash for the candidate block, then he wins the race and his block is approved as the new block to be added to the blockchain. Let's make a big detour to find out what his Bitcoin targeted number is all about. 1. The targeted number is set by the Bitcoin system. It is the number that a miner's candidate block hash must be equal to or less than the targeted number. In this respect, the term target is not really appropriate. Threshold is probably more appropriate. It is a number threshold that the candidate block hash must not exceed. 2. The purpose of this is to control the speed of the mining process, so that new blocks will be generated on average every 10 minutes. Bitcoin protocol is set at this speed so that the last block will be mined in 2140 to hit the maximum Bitcoin supply of BTC 81 million. 3. The hashing power of miners improve exponentially over time due to improved hardware and more miners coming in. This means miners will be able to discover the targeted number faster. In the early days, miners used CPU, or central processing units. They then moved on to GPU, or graphical processing units. GPU uses large numbers of arithmetic logic units which are used for rendering displays such as videos and computer games. Use of GPU has been mainly responsible for the exponential growth in computing power. New and more powerful devices further increase processing power, such as those using ASIC or application-specific integrated circuits. 4. The system has to reset the targeted number to fine-tune miners' changing hashing power and the level of difficulty to find the right candidate block hash. The system does this automatically after every 2016 blocks. This recomputation of targeted number is about once every 2 weeks so that the 10-minute block interval is maintained. 5. The targeted number sets the difficulty level for miners to obtain the right candidate block hash. The level of difficulty depends on how big the number is. The bigger the targeted number, the lower the level of difficulty. And the reverse holds true, the smaller the targeted number, the higher the level of difficulty. This logic is easily explained using the roll of a dice. Each number on a dice has the same probability of turning up, which is 1/6. If the target is set at 5, the chances of having a number that is 5 or lower with one throw, is 5/6, or 83%. Compared to if a target is set at 2, the chances that a roll will throw up a number that is 2 or lower, is 2/6, or 33%. Hence, higher number, lower difficulty, and vice versa. You can try it out with the dice video, stop and play to see the rolls. A further detour to numbering systems. There are many ways to represent numbers, in terms of sets. For our purpose here, let's just focus on 3 ways, namely the decimal, the hexadecimal and the binary. The decimal is our normal way of expressing in numbers, which uses sets of 10, with numbers from 0 to 9. Hexadecimal is expressed in sets of 16, with numbers represented from 0 to 9, A, B, C, D, E and F. Binary is expressed in sets of 2, with numbers represented by 0 and 1. Let's take for example the very first Bitcoin targeted number. This info can be seen in the header in the Genesis block. It looks like this. It is hexadecimal form which has 64 numbers. Each number is 4 bits, making a total of 256 bits. This is a very big number. In decimal form, it looks like this. In computers, the numbers are represented in binary form. The 256 bits in the hexadecimal will look like this. The purpose of this brief on math in electronics is to draw your attention to this point as regards Bitcoin mining. You may have heard or read in many Bitcoin narratives of miners trying to solve a mathematical problem. So what the miner tries to do is to get his candidate block hash value that is equal to, or less than the targeted number. It is described as a quest to find a number with the same or more leading zeros in the targeted number. This is technically incorrect. For the uninitiated, there is a lot of confusion over this. First, you need to understand, we are talking of the leading zeros in the binary form, not the decimal or hexadecimal form. If the candidate block hash has more leading zeros than the targeted number, it means the number is smaller and thus accepted. If it has less zeros, it means the hash is bigger than the targeted number, and thus fails. But if it has the same number of leading zeros, does it mean it's acceptable? The answer is not necessarily so. This is because the number is so big, one cannot tell from the leading zeros alone. One needs to know the actual decimal numbers. So the common narrative of finding a hash that is more or same number of leading zeros as the targeted number, is not actually correct. Technically, the quest is to find a candidate block hash that is equal to or less than the targeted number. Just to add on some more understanding. If you remember your high school arithmetic on floating points, deducting a leading zero increases the number, and increasing a leading zero makes the number smaller. In the case of binary form, which works on the power of 2, decreasing leading zeros by 1 doubles the number, whilst increasing leading 0 by 1 halves the number. Let's backtrack to Max and his candidate block. Now he has got his candidate block hash done. What is the probability of the hash value being equal to or less than the targeted number? It is practically impossible to hit jackpot at one try. What he needs to do is to rework his hashing until he is lucky to get a correct hash. But remember, any data that has a tiny bit of difference will throw up a different hash. And the same data will always throw up the same hash. So no matter how many times Max redo the hashing, he will always end up with the same candidate block hash since all his transaction data remains unchanged. To solve the problem, Max hashes the Merkle root with header of previous block, together with something called a nonce. Nonce stands for number used once only. This is an arbitrary number of 32 bits. If the first number does not produce a right hash, the nonce number is increased by 1. This is an iteration process. The nonce keeps on changing its number with each rehash. In other words, while the Merkle root and the previous block header are fixed, the nonce is variable. Thus Max can keep changing the nonce till he hits jackpot. Of course all this work is done by algorithm. It is estimated that for the block rate of 10 minutes interval to be maintained, the entire current Bitcoin miner network has to do 150 quadrillion iteration of the nonce per second. That's massive computing power at work. And massive electricity consumption. One thing to realize is this. For Max to hit jackpot with a nonce, that will produce the right candidate block hash, it has nothing to do with his methodology or computing power. It is a matter of pure luck. Just like rolling a dice. What happens after a miner has found the right candidate block hash? After the celebratory dance, miner Max adds a header to his candidate block. A block header holds certain data, one of which is the successful nonce number that Max used. With this info, other full nodes can use it to validate the block. The nonce proves the work done by Max. The header also contains the hash of the previous block, thus identifying the parent block. Miner Max next creates a TXO to pay himself the reward for solving the mathematical puzzle. This TXO is the first transaction in the block. The analogy is Max has mined the Bitcoin. Max then links his candidate block to the blockchain in his server. Next, Max transmits his candidate block to the network for discovery. Other miners pick up Max's block, propagate and validate it. The validation is checking all the technical criteria required by the system, which includes all transactions have passed the verification test. Using the nonce that Max provided, other miners can verify the new block hash. If miners find something not validated, they reject the block. If they find it is valid, they link the block to the blockchain in their own server. By adding to the blockchain, the miners signify their acceptance of Max's block. Acceptance is by consensus. If a majority of miners accept the block, Max's candidate block becomes the new block in the new blockchain. In this manner, The distributed network with thousands of independent servers ensure that everyone work on the same database known as the public blockchain. All miners will clear their mempool of transactions already mined in Max's block. All miners will drop their candidate block they were working on and immediately commence work to mine the next block. To sum up, the question is, what is the fuss of Bitcoin technology? The power of all this hashing to secure the data in the blockchain becomes apparent and the cascading impact of a hack. If someone makes a small change anywhere in the chain, it renders all the hashes after the affected block invalid. Thus a breach is immediately identified. In a distributed database, how does each independent server maintain the same database for users? This has been a big computing challenge in a distributed system, often referred to as two generals problem, also called Byzantine generals problem. Briefly, this refers to the difficult situation of two generals in a coordinated action. General A sends a message to General B that both will carry out the attack at a certain time. Both generals prepare to launch the attack, but neither knows whether the other general will actually carry out the attack. In distributed network, the individual servers do not know who is going to accept which new block. The proof-of-work methodology and consensus building enables the network of thousands of servers all over the world to end up with the same version of the public blockchain. Distributed network, blockchain, and proof-of-work are not entirely new. What Satoshi has done is coming up with the first application and his methodology for proof-of-work, that allows integrity of data in a distributed database environment. Thanks for watching the video. I have a favor to ask. I need to build subscriber base in order to monetize my effort here. So if you find the video useful, please subscribe and like and share with your friends by clicking the YouTube buttons below. Thanks a lot.